So we are studying weighted graphs, and we started looking at the shortest path problem, in particular the single source shortest path problem. And we saw Dijkstra's algorithm, and we said that it will work if we don't have negative weights. So let's see what happens when we have negative weights. So first let's recall Dijkstra's algorithm and look at it a little more formally than we did last time. So remember that we thought of Dijkstra's algorithm operating in this burning pipeline story. So we had these vertices as oil depots and we had the edges as pipelines. And if we set fire to a source vertex, then the fire spreads at a uniform pace along all the pipelines, and then we try to calculate the order in which each of the vertices will catch fire and propagate the fire further along new edges. So in the process of doing this as an algorithm, what we do is we keep track of which vertices have already burned, that is the vertices for which we have already computed the shortest distance, and we have an estimate about how long it's going to take to reach the others, so that we have what we call the expected burn time, which we keep updating as we go along. Right? So formally we keep track of these two things, the burnt status and the expected burn time. So initially we set the burnt status to be false. So let us call it B of j. So for every, or B of I, for every vertex I, B of I is initially false. And just to keep track of an auxiliary quantity, we will let U be, right? So U be is just the set of unburnt vertices here. So UB is just stands for unburnt, right? So UB is those k for which Bk is false. So initially UB is a set of all vertices. And the way we start this algorithm is we set the burning time of the source vertex, which we are assuming to be 0 in this case. We assume that the burning time of the source vertex is 0 and everything else has vertex burning time infinity, because we have no information. And then what we do is, as long as there are unburnt vertices, right, in this case everything is unburnt, so of course there are unburnt vertices, you pick up one of the unburnt vertices which has a minimum expected burn time. So initially there is only one, that is the source, right? So you pick up the source vertex and you update its status. So you update the status of the vertex you pick up, saying it's now burnt, right? So therefore in some sense its expected burn time is frozen as whatever it was now, and correspondingly the unburnt vertices will reduce, because this particular vertex that you have chosen to burn now is no longer unburnt. Now more importantly, what you do is you look at every outgoing edge from this new vertex. So you just burnt j, so you look at every jk edge and check if k is unburnt, that is we still haven't fixed its distance, then you update its distance to be the minimum of the distance you already know, right? So this is what you already know about k, plus the new information that you get if you process this edge jk, which may or may not have been taken into account before, obviously, because you have not reached this j before this. So you look at what is the time that you burnt j and how much time it will take from j to k, and this might well turn out to be smaller, right? So this is Dijkstra's algorithm. So now we looked at this correctness proof and we argued why we actually need this edge weights to be non-negative. So we said basically that we are incrementally discovering shortest path. So every new shortest path extends an earlier shortest path, and inductively the burnt vertices are those for which the distance has been computed and frozen. We are never going to update those things again. So at some point in the algorithm we have a big set like this, right? So we have this big set of burnt vertices. So all the vertices in this set, so we have the starting vertex, which now I have called S just to denote it, and then we have various vertices x, y and all that, which we have burnt so far. And what Dijkstra's algorithm now says is, among the remaining, look for the one with the smallest expected burn time, and it will turn out that that will be connected to some vertex in the set, right? So it will be connected by an edge. So it will be the minimum of something plus the edge from x to v. And the argument was that if we now choose to burn v and add it to the set and freeze its time at the current time, we will not be making a mistake. And that's because if we find a new path to v later, it will come through another w, but that w must also start from inside the burnt vertices. So when I burnt v, w had a higher expected burn time, right? So otherwise I would have burnt w. So when I get here, if I look at the cost of going to w plus the cost of going from w to v, it cannot be less than what I already have for v. And this crucially depends on the fact that this edge from w to v is not negative, because if it was a large negative edge, then going via w I could actually suddenly save a lot of cost when coming to v, right? So that's the crucial thing. So the argument does not work. So we cannot freeze the cost of a vertex the first time we burn it if we are allowed to revisit it via a negative edge later on. So that's why Dijkstra's algorithm requires non-negative edge weights. So the difficulty is precisely this, that we stop considering updates once we burn a vertex, right? So what happens if we start allowing updates even after we've burnt a vertex? So then the notion of burning doesn't really make sense. So this analogy that we have doesn't really make sense, but it is a plausible strategy. And why is it a plausible strategy? This plausible strategy because though we are allowing negative edge weights, we don't have any negative cycles. So this means that if I am going from, say, the starting vertex to some vertex x, right, it cannot help me to go through a loop, because every loop is guaranteed to have a non-negative weight because there are no negative cycles. So if I want the shortest path from any starting vertex from the starting vertex to any other vertex x, I may as well assume that that path is really a path in the sense of we have defined, that is, it has no loops, it has no repeated vertices. So if it has no repeated vertices, right, then what we can consider is in terms of the length of the path, not in terms of the weights of the path alone, but we have the shortest path which takes us from, say, 0 or source vertex to a vertex k. So not only is the weight minimum, but the reason that this is the path I chose is because there are no shorter paths which have the same weight or less, right? So it need not be the shortest path overall. We saw examples where you could have one edge which takes me with 80, but then if I take two edges, I might go with 10 plus 6, 16. So the shortest path might well be a roundabout path, but what we are saying is that if there is a path of length 2 which is shortest, there is no path of length 1. That's what this means. So this is so L, if I have to do this, I have to take these L steps in order to get to k, and there is no better way of getting to k to achieve this cost, right? So this is not the minimum number of edges for going from 0 to k without considering weights, but it is the minimum number of edges and the shortest weight if you consider weights. Now here we again go back to our old argument which says that, okay, if this is my path, then what happens when I come to J1, right? Could I have come to J1 any better than using the weight W1? Well, if I could have come via a different route and come less than W1, then I could come to J1 and then continue with the same path to K, right? So if I could come to J1 earlier than I have now, then I could use that path plus the path from J1 to K and get a shorter path to K. So if this is the shortest path to K, then this must also be the shortest path to J1, the shortest path to J2, the shortest path to J3 and all that. So every prefix of this path has to itself be a shortest path. So this gives us a starting point to think of an algorithm to deal with negative edge weights, right? So in some sense, once we have updated this one, right, once we have found the shortest path to JL-1 by some algorithm, then we know that the update that we get for k is going to be a final update. There is not going to be a better one than that, because if I keep decreasing, right, I can only decrease up to the shortest path. I cannot go below the shortest path. And when will I hit the shortest path? When my nearest neighbor which feeds that shortest path is also frozen. So in some sense, if my neighbor's shortest path is known, then my shortest path will be known in the next step. So therefore, for that neighbor's neighbor should have been known in the previous step. So we can try to see if we can fix these shortest paths one at a time. If I can fix J1, then I can fix J2. If I can fix J2, then I can fix J3 and so on. And once I fix JL-1, then I can fix K, right? So what we want really is an algorithm which tells us that after we have done L updates, right? So an update for us is what we did when we burnt a vertex. When we burnt a vertex, we reset the burning time to be the minimum of what we already had plus the new burning time we discovered through the recently discovered vertex. So if we can guarantee that after we have done this L times, we have actually made sure that there are all paths of length L are at their minimum. There are no shorter weight paths of length L. Then since there are at most n-1 edges, then if we do this n-1 times, there are no paths without repeating vertices, the strong notion of a path. There are no paths which have more than n-1 edges in them, because once you take the nth step, you have to repeat a vertex, right? So if we have this property that we can update and make sure that after L updates, all the paths of length L in terms of number of edges have achieved their minimum, that is, there are no shorter ways to go in L edges or less. You have to take maybe one more edge and take a negative edge, that's different, but you cannot get there in L edges. Then we can guarantee that we can sort of first find all shortest paths. So this is like a combination of breadth first search which finds shortest paths by length of path, right, and our weighted thing which finds it by length of weight. So what we are saying is that up to this path length in terms of edges, there are no shorter paths in terms of weight. This is the kind of property that we want. So this algorithm is called the Bellman-Ford algorithm, right? So it's a much simpler algorithm in some sense than Dijkstra to think of, although it requires a little bit of understanding like we just did to see why it works. So all we do is we, like Dijkstra, this expected burn time, right? So we keep track of the distance to every vertex as far as we know so far. So initially the distance to the source vertex, which again we assume is 0, the source vertex is 0 and its distance is 0, and everybody else's distance is assumed to be infinity. And now comes the update. What Bellman-Ford does is just n minus 1 times, it just blindly updates everything, right? So it takes every edge and it looks at the starting point at the edge and the ending point of the edge, right? So I have an edge which goes from say some j to some k. So there is currently at this iteration there is some distance that I have associated with j, and then I have associated some distance with k, and I have what I would get if I take this edge and append it to j, right? So this is a candidate to replace d of k. So that's what we do. We just check for every k whether the weight that the distance that we have currently assumed for k, is it smaller than the distance that I would get if I take one of my neighbors and add that edge weight from that neighbor to that distance, right? So I just blindly do this n minus 1 times, and the claim is that this will actually give you the shortest path, right? So this actually works for both directed and undirected graphs. So the example we did for Dijkstra's algorithm was for undirected graphs, but you could as well do it for directed graphs, because anyway we are following edges in one direction only when we compute the shortest thing. So let's look at this example. Okay, so this is a directed graph. It has some negative edge weights like -4, -1, right? And there are arrows in this, right? So there are some, so you can go for example from 0 to 1, but you cannot come back from 1 to 0 and so on. So let's see how this Bellman-Ford algorithm would work on this. So what we do is we keep recomputing this distance d of v. So remember that d of v is the best distance I know of right now for vertex v. So in this case there are 8 vertices 0 to 7, and we are going to iterate this thing after initialization n minus 1 times. So there are 8 vertices, so n is 8. So we are going to run this algorithm, this iteration 7 times, and in 7 times it should hopefully give us the shortest path from 0 to every other vertex. So we initialize it by setting the distance of 0 to the vertex 0 to 0 and everything else to infinity, right? This is our initialization for Bellman-Ford. So initially we know nothing about how to get to any other vertex, and now we do this update. So now we look at every vertex, or we look at every edge is how the Bellman-Ford algorithm says. We look at this edge and we say, okay, what do I know about the starting point plus this weight versus the ending point, right? So the update is compare d of 0 to d of 0, sorry, d of 1 to d of 0 plus the weight of 0, 1, right? So what should I put here is the question. So should I leave it as what it is, or should I update it by some new information that I've got about the edge coming into it? Of course I could do it for d of 2 also, but then I know that for d of 2 and d of 6 nothing has happened because everything is infinity. So it's really d of 0 which carries some importance at this stage. So if we do this, we find that from 0 I can get to 1, and from 0 I can get to 7, and therefore the entries for 1 and 7 get updated from infinity, which is what I knew before, to 0 plus 10 in the case of 1 and 0 plus 8 in the case of 7, right? So I updated to the time to reach 0 plus the weight of the edge from 0 to that vertex, and everything else is infinity because I can't reach it from 0 at this point. But now I have some information about 0, 1 and 7. So in the next step I can look for any vertex which is either connected to 7 or connected to 1, right? So not that one, but say this one, right? So 1 is connected to 5. So in the next step what happens is that because 1 is connected to 5, right, and I know that I can reach 1 at time 10, then in 10 plus 2 I can reach 5 in time 12. Earlier I believed it was infinity, so I can replace it by 12. In the same way, if I look at 6 for instance, right, earlier I thought it was infinity, but now I know that I can reach 7 in time 8, and 7 plus 1 is 9, 8 plus 1 is 9, so therefore I can reach vertex 6 in time 9, right. So these two things which are connected to the vertices I recently burnt get updated. So we keep doing this. So now we have burnt 6 and 5, not burnt, but we have updated 6 and 5 in addition to 0, 1 and 7. So now we will find new paths because 6 also has outgoing edges. Okay. So in particular now what we will find is that there is a strange phenomenon that we have discovered, which is that if I come from 6, so remember that 6 had been assigned 9 before, right? So right now these are the numbers that we have. Everything else is infinity. So now if I'm at 9 and if I take this negative edge, then I can actually come from 0 to 1 at cost 5, right? So instead of going directly in cost 10, which is what I had earlier assumed, I could take this roundabout route, right? And I can do 8 plus 1 minus 4 and come there in 5. So this is the kind of update that Dijkstra's algorithm would not have discovered, right? Because it would have really frozen that thing at some point, saying that it's already given and therefore I will not update it. So this 10 becomes 5. Okay. What about 2? Well, now 2 I can reach from 5, so it's 12 minus 2, so this becomes 10. Right? And 5 itself now is interesting because earlier I had to come this way and that was costing me 12. But now because I can come from 6 directly, right? I can come to 6 and 9 and then 6 to 5 will give me 8. So this has become 8. So in this way we keep updating, right? So now after this, now that I know 2, I can even update 3 because 3 is reachable from 2. So if I can reach 2 in time 10, I can reach 3 in time 11. But of course 2 itself has now got a better route because having come to 5 in time 8 now, right? Remember it was 12 and then it became 8. Now I can go from 5 to 2 in time 6. So basically each time I'm looking at the previous row, right? So the fact that 2 gets updated from 10 to 6 now does not yet reflect in the fact that 3 should be updated. Okay, so 3 is updated from infinity to 11 because I knew that 2 was 10 before I did. So all these updates are happening at this time based on the previous time's information. So I'm not doing it in sequence in that sense, right? So though I calculate that the distance to 2 is 6, I don't use it to calculate the distance to 3 is 7 yet. I will do it in the next round, right? So in the next round, I discover that 2 was frozen at 6 and therefore now D has become 7, right? And finally, I've also found something that reaches vertex 4 because now I've got this path which goes this way, or there are other paths also, right? So we have this path also which goes this way and so on, right? So we have many paths which come to 4, but I only now reach that and I calculate 14. So I keep iterating this and I get slightly better paths everywhere. And finally, after I have done this 7 times, right, I have discovered a stable thing, and you can calculate that if you do this one more time, you should actually get no updates. Right? There should be no shorter paths if there are no negative cycles. So this is how the Bellman-Ford algorithm works. It just keeps updating every vertex every time, and you do it a fixed number of times, which is the number of vertices in your graph minus 1. And once you have done that, you're guaranteed that all the paths have stabilized. So what would happen if there was a negative cycle? Well, the paths would not stabilize, right? There would be a way to take a path longer than n minus 1 edges, go beyond that and go around a cycle and get still shorter, right? So if I iterate this one more time and the distances decrease, right, then I know that there is something wrong. So this is one way. So either you can assume there are negative cycles and keep running it, or you can run it, and then when you come to the nth iteration, which you normally should not need, you need to stop with n minus 1, but you can run it one extra iteration and see if you get a decrease in the distance, and if you get a decrease in the distance, that means there was a negative cycle, right? So check that the nth update should not reduce any d of v. If it doesn't reduce once, then after that, once the d of v is stabilized, there's going to be no update because the previous update is just going to propagate. So once I get the column repeating, there's going to be no change further on. So if the column changes at the nth step, then you know that you had a negative cycle. Right? So we saw Dijkstra's algorithm, and Dijkstra's algorithm assumed non-negative weights, and the reason that we needed that property was because of this this strategy we used to freeze the distance to burnt vertices once they were burnt, right? So we never looked for updates to that, so we should not have found any new updates through negative edges, otherwise that strategy is not correct. But assuming that we don't have negative cycles, remember if we have negative cycles, the notion of a shortest path is not defined because you can go round and round the cycle and you can make a shortest path as short as you want. Right? So the shortest path is defined only when there are no negative cycles, even if there are negative edge weights. And in such a case, what we just said is that the shortest path is a path. It cannot involve a loop, right? And every prefix of that shortest path is also a shortest path. And you can use this in this Bellman-Ford algorithm to iteratively find the shortest paths of length 1, of length 2, length 3 and so on. And after n-1 iterations, you've automatically found shortest paths to everything. So in a way, Bellman-Ford is a much simpler algorithm to think of. It's just a blind iteration. You just n-1 times you keep updating, right? You don't have to keep track of anything that was burnt, and you don't have to keep track of expected burn time separately and all these things. You just keep updating. Every time you make an update, you look at all the neighbors and update them again. And the property of this fact that the shortest paths are monotonic, in the sense that every path is an extension of a shortest path, guarantees that after n-1 steps, all these updates will converge unless you have a negative cycle. So you can also use this algorithm to find negative cycles in that sense. If you go through this whole process and you do it one more time and you find a decrease, then you have a negative cycle.